I'm going to say a little bit more about the physics of solar cells, or photovoltaic solar cells. And this is a reiteration of what was stated earlier. On this picture here, you'll see that there are silicon atoms, or represented by the black ones, and then the impurity that's purposefully added for the what's called the n-doped silicon. We're going to add to it something that's more negative, has more electrons in the valence level than silicon does, and that's phosphorus, typically what's used. So maybe one in every several thousand atoms in the matrix that you see is a phosphorus atom, and that contributes an extra electron. So it bonds, and that has this extra electron that in some cases can float around. And that's what the n-type material looks like. And then you have, as I mentioned earlier in the previous video, you have a p-type material as well. And the p-type material, that is typically boron, will have 3 valence electrons. And so in the p-type material, you have a hole here. Now note that this is still neutral and that's still neutral, but you have an excess of free electrons, you can think about it here, and an excess of free holes here, or absences of electrons. So naturally, the electron that's on this side wants to go to the hole on that side, and vice versa. And I guess you can think of when the electron moves, the hole does as well. And so then you get this region that's called a diffusion region in between the two materials, which would be somewhere in here, where you have electrons kind of invading into this side and holes invading into that side. And then at the same time, that causes the corresponding side to have a net charge. Again, this is neutral here, and that's neutral. But once these electrons over here move to here, and the holes over here move to there, then this becomes net positive, that becomes net negative. And so then you have a desire for the electrons to come back. And it's the balance between those two forces that maintains an equilibrium. Until you put the solar cell in sunshine. When you put it in sunshine, and then the sun's strong enough and has the right frequency, and light is of the right frequency to the visible light, will get these electrons, more electrons released from here. And then when more electrons get released from here, as long as there's a conducting path over here that circles back to here, those electrons are going to want to go this way. They can't go that way because they're going to be fighting upstream. They're going to be pushing this way once they get released from the sunlight. So it creates basically an extra current, or it enhances the degree to which the electrons are going to be repelled from this side and go this way. And so then you get this current when there's light. And the more intense the light, the more electrons are going to be released, and the more current you're going to have. So that's why you want to have your solar panels in bright sunlight. And the next few slides really just emphasize the points that I was just making. So I'll go through them relatively quickly. And then the junction between the N and the P-type material, or the P and the N-type material, is called a P-N junction. And this is an incredibly important technological advance that happened in Bell Labs. It was actually either the late 40s or early 1950s, but it was the invention of the transistor that also came with it the solar cell and the diode, which we'll talk about soon too. So in the dark, again, we said this earlier, the diffusion current and the drift current balance each other out. But then if you shine light on the N-type material, which is this stuff here, you get those extra electrons, which then creates a drift current. It makes the drift current stronger, and you have these electrons that then start flowing out if you have a path for them to follow. A wire, basically. So you have to have a lot of wires engraved into the N-type material here, and then a metal plate on the P-type material. So if you see a solar cell, on the surface of it you'll see all these little strips of metal. That's what that is. That's the N-type of material. That is the path that the electrons can flow. Again, that happens when there's light. And then what's actually interesting is there's each little cell that we have in a solar panel, when light's shining on it, it can produce 6/10 of a volt. And that's due to the physics of the, basically of the p-n junction in terms of the buildup of electrons on one side and holes on the other. That is actually creating a voltage. But that will create 0.6 volts. And that, no matter what the current is, it'll create that same voltage, which is interesting, which will lead to characteristics we'll talk about later. And so if you want to build up a greater voltage, what you're going to want to do is string a bunch of these together. And then you can see that on some of these pictures here, where if you want to build up voltage or build up current, you either put solar cells in series. Putting them in series will cause those 0.6 volt drop across each one to add up. So you get 1.2, 1.8, 2.4, 12 volts, 24 volts. However many you put in series is the voltage you'll get. And if you want to increase the current that your solar cells will provide, then you put them in parallel. So you do a combination of series and parallel on these solar cells to get whatever voltage you're looking for. Here's an example of a couple that are in series, where the voltages can be twice the voltage of each one. And of course, if they're in parallel, then you get more current. And this is what a typical panel will look like. Many panels are designed to charge 12-volt batteries. In the solar kit, which, as I told you in other videos, students used to wire together, that would be used to charge a 12-volt battery. And there's a standard configuration of solar, certain number of solar cells in series, 36 of them in series, that will allow up to 22 volts. And the reason is because sometimes you don't get that full 0.6 volts. Might be a little dark out. There's a lot of reasons why you may not get the optimum 0.6 per cell. So to allow for making sure you have 15 volts that you'd want to have to charge 12 volts, very often we put extras in there. So it's kind of like adding insurance to make sure that you get enough voltage out. And you can build up as many as you want in series and parallel, as long as you have them, to get large currents and voltages, and therefore the capacity to power devices that demand a lot of power. And so in this example here, if each of the 12-volt panels is 12 volts and 36 watts, the question is, what would be the voltage of the array? Well, you take this is 12 volts, 12 volts, 12 volts, 12 volts, and you can say that for each of these branches. If you add up all of those together, you'll get 48 volts. And the power of each one is 36 watts. That means that the current that each provides is 3 amps, using power is equal to, power divided by voltage would be current. That's what the second equation is telling you. So if they're each providing 3 amps, each of these branches, you could say, 3 times 3 is 9. So 9 amps total is going to be what this configuration produces. 9 amps, 48 volts. So if you want to know the complete power that this could generate, you multiply the voltage times the current, and that gives you the 432 watts. So you can get some pretty high, that's not necessarily all that high, but if you have enough of them together, you can get arbitrarily large numbers. And note that solar is DC. That means the voltage doesn't vary and the current doesn't vary. AC systems do vary, and that's what you get from the wall. And we'll talk more about why we use AC rather than DC. But when you see AC, that means alternating current, which means the current, if you could look at it versus time, it's actually varying like a sine wave. 60 cycles per second in the United States. And if you looked at a battery versus time, battery voltage, it would be constant. That's DC. Same thing with a solar cell. That would be DC, constant. You can convert between them if you need to. And then in most solar systems, you have solar power, and you have to have something that is charging the battery. You can tie this directly to a battery, a solar panel to a battery, and charge the battery that way. But this charge controller is kind of like the smarts behind a solar system. A solar system being a system of solar panels and batteries and things that you want to have those power. This knows when the battery is low, and it tells the solar panel to supply the battery with current. So this thing provides some smarts. So the battery is charged in the right fashion to optimize its performance. And it can also allow devices to run as well. And so that's part of what the charge controller does as well, is it decides if the battery is strong enough to let devices run. If you want to use AC power, then you have to use something called an inverter that'll convert DC to AC. If you ever want to do that, you can. Off your car battery, you could run things that are in your house if you have the right inverters and systems that allow for that. And then you can get solar installations of all sizes. You can get small solar installations that might be used for pumping water, just for single person or single family's use. Only work during the sunny day, because if there's no battery, that could be a really simple system. Could be used for supplying light at night for people who may not have electricity available to them. These are all considered off-grid solutions. And some people build a house that isn't on the grid. I know people in Big Sur. PG&E doesn't go to some spots. So if they want electricity, which most people want, they have to set up their own systems of solar panels and batteries that will allow them to store the energy that they can get from the sun. And even small communities can do that. You can have a number of houses that are all using an off-grid system, where none of them are connected to the PG&E or to whatever power supplier they have. You can also have, and this is an example of the community right here. And you can also have systems like what I have on my house, where I have solar panels on my house that actually feed directly into the grid. And I get my power from the grid, meaning PG&E, but I get paid for the energy I produce. In other words, it reduces my PG&E bill. So I'm actually a producer of energy just by living in my house and having solar panels on my house. And the U.S. power grid is how we get energy from one place to another. It's very complicated. It's evolved over time. And its humble beginnings were in the 1880s, 1890s, when you had somebody who was providing power from a waterfall, somebody who was using it a few kilometers away, and it just kept growing and growing across the country and different parts of the country, and then connecting them. And now one part can provide energy for another in some cases, so it's very intricate, very involved. This involves what I said, I get paid for producing energy. That's called net metering. So I'm actually an energy producer at my house, and you could be using the energy I'm producing. You don't know whose energy you produce, whose energy you use, but it's green energy. So I didn't have to burn any coal to produce the energy I'm using right now. It all came from the sun. And some utilities are actually getting really large installations of solar cells, solar panels, that will allow them to provide solar energy to hundreds, thousands, millions of users. That's the idea. But that has an impact also, because it takes a lot of area to collect all that energy from the sun. So it becomes a balancing game, and it doesn't work at night. So at night, you have to have a backup or something else that can provide energy when the solar is down. Batteries are great, but batteries at that capacity and that size are difficult to procure. And then the solar suitcase this is the thing that I had my students wire up. This will provide enough energy for a person, maybe a family, to use energy at night, and can store it in a little battery and collect it from a solar panel. And this is how it works. During the day, the battery is charged. At night, the battery provides energy, or after the battery is full, you can get energy directly from a solar panel to something that's using it, maybe a cell phone charger. And then at night, the battery provides energy that is used for different appliances. That's all for this video. I will talk about efficiency a little bit more in one more video about solar panels and solar energy. All right.